Good morning, students. Today we are going to see the next very important topic from the first unit, that is series RLC circuit and its quality factor. So it is a very important big question, part B question. Here in this network we will be having all the three components, passive components, that is resistor, inductor and capacitor, connected in series with each other. So here in this circuit we were discussing about what is the condition of resonance. At resonant condition, how the circuit will react, and then finally we will be discussing about its quality factor. So saying about this topic, here we will be discussing all the parameters related to frequency. Generally we will be discussing about the circuit in time domain with related to time, whereas since we were focusing on resonance and since we are going to use this circuit in RF circuits, so here we are going to discuss the circuit with correspond to frequency. So in correspond to each component we can see the resistance and reactance values. So first we can see the resistance, reactance and impedance values of the components. After that we can discuss about the voltage, current, then we can proceed towards the frequency, bandwidth, and finally we can discuss about the quality factor. So saying about the inductance, the inductive reactance can be referred as, that is XL is equal to 2 pi FL. So next we are saying about the capacitance, we can say the reactance will be XC equal to 1 by 2 pi FC. So both are reactance, both inductor and capacitor creates a reactance, that is storage effect. So since it is in series, they will cancel each other. So in such scenario, if you want to see which is dominant, then by seeing the reactance value, that is when XL is greater than XC, the circuit we can call it as inductive, and when XC is greater than XL, the circuit we can call it as capacitive. So when we want to calculate the total circuit reactance, we can say that is XL minus XC or XC minus XL based on which is having higher value. So if you want to calculate the impedance value with correspond to reactance, we can calculate as Z is equal to root of R square plus J XT. So XT, that is total reactance. So next we can see about the voltage. So what about the voltage in the series resonant circuit? So saying about series circuit, here the supply voltage is Vs and each component they will have the corresponding voltage drop. So summing all the voltage drops in the circuit components is equal to the supply voltage. So this is the condition of series circuit. So from that we have written that Vs square is equal to Vr square plus VL minus VC whole square. That is based on which, that is here the inductor is dominant, has higher value, or when correspond to when saying about capacitor, so VC minus VL whole square. So like this, to correspond to the reactance value, the voltage can be referred. That is supply voltage is equal to all the component voltage drops. So summing all the component voltage drops. So next we can discuss about individually what about the reaction of reactance with the correspond to frequency. When saying about inductive reactance, when analyzing the characteristics with correspond to frequency, the graph, if you are seeing if you are plotting the graph with the correspond to frequency, it will be straight line and it is linear curve, and it will be a linear, so linear straight line. So if we are seeing the graph, that is the characteristics, if you are plotting between the reactant inductive reactance and frequency, the graph will be getting a linear straight line. So, and if you see about the reactance, the graph, it is positive and it is directly proportional. That is the reactance, the inductive reactance will be directly proportional to frequency. Inductive reactance will be directly proportional to frequency. So next, thinking about capacitive reactance. So capacitive reactance against frequency, that is when we are seeing about capacitance, that is actually the frequency, it is the the frequency will be inversely proportional to reactance. So inversely proportional. So when we are simplifying this, we will be obtaining in an exponential form. So the characteristics for graph, what we obtain will be a hyperbolic curve. It will be an hyperbolic curve. So, and another thing, it will be inversely proportional. So it is in a decreasing form. So it is negative. So here the reactance is, can we say it as negative. So next we can see about when we are seeing about two reactants at resonant condition. At resonant condition, what we are saying, that is XL is equal to XC. XL is equal to XC. So when we are plotting this, at resonant condition, the inductive reactance cancels completely the capacitor, and both are same. So that condition we will call it as resonance. So, and the frequency, that frequency we will call it as resonant frequency. That frequency we will call it as resonant frequency. So when we are seeing about the linear frequency, linear resonant frequency is equal to 1 by 2 pi root of LC. So when we are saying about angular frequency, that is equal to 1 by root of LC. So next, what is the thing when series circuit? What is the next we can see about the current? So when we are saying about at resonance, XL is equal to XC. XL is equal to XC. What will happen? Both the reactants cancel each other. So the storage effect will be zero. The storage effect will be zero. There is no drop across the inductance and capacitance. There is no drop across the inductance and capacitance. So the current flowing through the circuit is decided by the resistant value alone. Purely the resistant value alone. So the current can be written with correspond to when we are seeing about it, the current will be at a resonant condition, that will be the maximum current, and it will only depends upon resistance. So we can say I is equal to V by R at resonant condition. Rest of the time, if we want to calculate what will be the current, then we can say I is equal to V by root of R square plus omega L minus omega C whole square. So with this formula we can calculate what is the current flowing through the circuit. So next we can see about the phase angle of the resonant circuit. So when we are seeing about the phase angle, if the capacitive reactance is more, then we can see the current will leads the voltage. The current will leads the voltage. When the inductive reactance is very high, then the current will lag the voltage. The current will lag the voltage. When both are, when XL is equal to XC, when XL is equal to XC, there is no resistor, no reactance, only resistance is there. At that time, if you see, the voltage and current are in phase with each other. So only at resonant condition XL is equal to XC. So it cancel each other, and only the resistance value alone be there. So what will happen? The voltage and current will be in phase with each other. So next we are saying about bandwidth. So bandwidth, bandwidth is the range of frequency. Bandwidth is the range of frequency, and the lower we will be call it as lower cutoff frequency, and upper we will call it as upper cutoff frequency. So the bandwidth can be calculated, that is with the help of the formula, that is FR by Q. So that is resonant frequency by quality factor. So otherwise we generally we will say bandwidth as higher frequency minus lower frequency. So when we are saying about bandwidth at resonant condition, at resonant condition, the reactance will be 0. So the maximum current will be flowing, I is equal to VR. So here from this bandwidth, with the help of this bandwidth, we can calculate the quality factor. If we want to calculate the lower cutoff frequency, we can say WL is equal to minus R2 by L plus root of R divided by 2L whole square plus 1 by LC. And when we are saying about upper cutoff frequency, WH is equal to plus R 2L plus root of R by 2L whole square plus 1 by LC. So with the help of this formula we can calculate what is the lower cutoff frequency and upper cutoff frequency. So when we are saying about what is the resistance value, the bandwidth may differ with the so different conditions can be obtained by changing the resistance value. So finally we can discuss about the quality factor. When we are saying about quality factor, Q is equal to, you can calculate with the correspond to inductance or capacitance, any component value, it can be calculated. That is we can say we can calculate the Q factor, that is omega L by R. Otherwise XL by, we can say XL by R. Otherwise if you are calculating with the correspond to capacitor, 1 by omega or CR. Otherwise if you are calculating otherwise XC by R. Else if you are considering both inductor and capacitor, then we can use the formula 1 by R root of L by C. So quality factor, that is the sensitive, we can say that is Q is equal to omega by, that is energy stored by energy dissipated. We can quality, if you want to define the quality factor can be defined as energy stored by energy dissipated. So that is the selectivity of the circuit. So I think this is the thing we want to analyze, we want to learn from this. So in this series circuit we are supposed to discuss about voltage, current, after that relevant to frequency, that is resonance, that is frequency, bandwidth. Finally we will be discussing about quality factor. So okay, so next we can see about the one problem relevant to series resonant circuit.